All right, so today we are going to start our discussion on performance because we are one thing that we care about and one of the motivation why we study computer architecture because we want our code more performant. So to begin with, today we are going to talk about what matters to performance to make it perfect. But before we start, it's always a good idea to remind us where we are coming from. So in the last lecture, we talked about the big picture of computer architecture in a way that everything, every computer, every modern computer that we have nowadays are so-called an implementation of a von Neumann architecture in some sense. So when we talk about von Neumann architecture, two main components at least you have to have those in your mind. The first one is the processor, and the second one is the memory. And but nowadays it's hard to imagine that a computer works without persistent storage. So that's why I also included that persistent storage in this big picture. And what will happen is that after you compile the code or after your runtime system generated the machine code, it's either first stored in a persistent storage, or if it's a runtime generated code, then it will be dynamically loaded into the memory immediately. But whatever is that when I want to run a program, the machine code and your data have to first be presented in your memory. And then what would happen is the processor would load instructions from the memory space that store the instruction and then look into what the instruction really want me to do. And depending on the context of the instruction, the processor would perform differently. So if it's a memory access instruction, then the processor would initiate a data access request to the data portion of your memory. And after we are done, what would typically happen is that the processor has to fetch the next instruction from the memory again. So here you can see this processor and memory, they are tied together to each other. And without the memory, there is no way that the processor would know what the program really wants me to do. However, without the processor, there's nothing could be done. So they are the essential of computers. And however, there are many ways of implementing computers. So for example, I can definitely have each key tied to a specific command of the processor and without having a memory, right? So that's pretty much your calculator. So calculator is the most, I would say, ancient form of computer in some sense. And that's exactly why we built computers. Because if you remember the history of computer, the very, very early computer is to solve the differential equation. Right, so it's meant to be a calculator, a more complex calculator. And for that kind of calculator, you have fixed function. However, we figure out this thing could be beneficial to a lot of our applications, very complex workloads. So that's why we try to make the computer more and more general, wanted to do more and more things. But in the meantime, von Neumann find there is a more elegant way of doing it. That's actually just having the abstraction of memory and processor. And all you need to do is to put different stuff into the memory, and then your computer can potentially become a gaming machine, a Bitcoin mining machine, data mining machine, a machine learning machine, or a word processor. Right, whatever you want to do, and if you want to do a calculator, it can also do that. All you need to do is to load different stuff into the memory, and you are done. But in the past, if the user interface is directly tied with the processor's features, then the only thing you can do is to reconfigure it in a hardware level, which is very inconvenient, and that's something that we don't want. So, however, there is another thing called the theory of computation or computational complexity. And a lot of algorithms professors, and when you design software, that's something that would first pop up in your mind. However, in several demos that I showed in the last lecture, I'm telling you, those are theoretically true in a way that if you have a very ideal machine, which every instruction takes exactly the same amount of time, every operation, every statement in this algorithm would produce the same amount of instruction, then it will work. However, is it possible? And the answer is definitely a no. So what does that mean is that a lot of stuff you learn in algorithm, they might not be useful in practice. So, and that's why we need to learn computer architecture. So before we talk about the first topic, performance, right? So, you know, how do you define performance is really important, right? So how good can be coded as perfect, right? We played the song Perfect before the lecture, right? I put that on purpose, right? So what is perfect, right? So typically people would say, hey, mine is better than yours, right? And mine is the best, right? So one thing, like when you apply, I mean, a lot of you are here as grad students, and you definitely went through the process of applying to grad school, right? So one thing you will pull up is the ranking, right? And I know you chose UCR for a reason. And I can always fine-tune some ranking to prove UCR is the best as well. So for example, okay, if you take the best national university rankings from the US News, it will tell you it's Princeton University. And when you apply to grad school, you will say, hey, I don't care about the general ranking. I'm a computer scientist. So let me figure out what's the best computer science schools. Then MIT pops up, right? And you know, I graduated from UC San Diego, and I can always find a ranking saying, hey, UC San Diego is the top one, right? And even UCR, we can also find we are the best for social mobility, right? So here's the thing. There are several ways of judge performance, right? But when we want to compare things, we need to find a standard of compare things to say this is better, this is the best, we are doing good enough, right? So the first thing I want to talk about today is what's the definition of performance? And then I'm going to talk about the equation of evaluating performance. And then we will talk about what would affect each component in the performance equation. So that's what we are going to cover today. So the first topic, what does that really mean by better performance? So we mentioned this class we are going to have peer instruction, right? So now, to begin with, let's have you get ready with peer instruction and have an orientation of what peer instruction is doing through this simple question. So now, first of all, let me see. Please. So before we start, right, here's the context of the question. So last lecture, you already experienced there are two popular generative AI who can chat with you during the midnight, or who can chat with you when you are confused about homework, right? And I don't know if any of you try to use it for reading quizzes, and I'm not sure how useful is that. But here is Gemini and ChatGPT, right? So pay attention to how they look like right now and what their reaction to the question that I've been asking. So I think the question that I have been asking is that what's the most popular in computer science, right? Which is part of the lecture in the last time. So that's the question we have today. That's the context we have today, and for now. And after that, right now, the second thing I wanted to do is make sure that you log into your Poll Everywhere through your app or the website with your UCR email. And here's the QR code if you are using an app or a website. And now, you have at least 90 seconds to answer the following question. And there is still a QR code on what? Okay. No, the QR code is on the top left. Yeah, you still have the QR code on the top left, or if you want to type in the website, it's on the top right. So right now, try to answer this question in 90 seconds. What kind of issue? What? Well, you have to log in with your UCR account. You have to log in with your UCR account.
It asked me to enter the previous username.
Well, that's on the top right. So did you visit that address? So I already see 15 of you answered. On the top right. PoolEV.com. Yeah, it's on the top right. So you have to address that with the IT, because I don't think there's anything I can do with that situation. Or you can use the app. Did you type it right? You type it wrong. H-U-N-G, not H-U-A-N-G. All right. Question? Issues? No? What happened? Okay, so if they ask you the name, that's on the top right? PoolEV.com/HongWeiZhen. Did you see that? Yeah. Yeah, you have to type that. I don't know about this because typically the registration required is because you link to the wrong account. Okay, so for people who have issues of login, you probably have to figure out how to address that. In some sense, like I don't know how to deal with that because I think the school changed the setting all the time, and the IT always have issues with that. So, and that's not something, the account related issue is not something that I can deal with.
It's pretty good on laptop.
What?
It's pretty good on laptop.
Well, but she has problem on the laptop. But are you okay with the app? Okay, so if you are not okay with both your app and your laptop, it means that there is something wrong with your account, right? So maybe some of the features on your account is blocked.
At least with the app, what was it? Scanning the QR code doesn't work, but if you type it in.
Oh, if I type it in, it will work? Okay, so maybe the QR code has something wrong?
Yeah.
Okay.
When you scan it, it like fails, it fails. But then if you type that in, it works.
Okay, so try that top right address.
Yeah.
Are we okay? Are you good? Okay.
I don't know. That's why.
Okay, last 15 seconds. All right, so here we go. So the first question that we have, it shows that, okay, it's still moving, right? So 32 of you answered on the top right, as you can see. And 47% of you think it's, 48% of you think it's C. So it looks like C is the most popular answer. So that's C. So now, and also like D is very popular, right? So now let's grab a few people around you and discuss with the most popular answers, or if you insist your answer is the most correct one. So try to grab a few people around you and discuss it for another 90 seconds, and don't forget to vote again when you guys reach your consensus. So now, go talk to each other.
Because ChatGPT has like a stream of information, whereas like, Gemini's like it's on or off. Like there's an output and there's not.
So if it is not.
All right, so every time when you hear that bell sound, it tells you that we are close. So if you haven't vote right now, because this also count, right? And there are only 16 of you voted, and so vote right now. I will give you 5 more seconds. 5, 4, 3, 2, 1. Time is up. Okay, after discussion, let's see, what do you guys think? Okay, so now, it's still pretty a tight between C and D, right? So at least a lot of you agree that 2 of them are correct. And let's check what are the 2 of them, right? So, okay, the 2, okay, first of all, how many of you think the response time Gemini outperforms ChatGPT? Okay, what is response time?
I think if you go by response time as just how fast you get an output, I actually think ChatGPT has a better response time because it immediately starts outputting, whereas Gemini waits to give any kind of response.
Okay, so here's the thing, right? So how many of you ever tried to ask a question through email with a professor or a TA? Right, you must do that a lot, right? So, okay, so let's say you have 2 TAs. TA1, that's called TA GPT, right? And the TA GPT, he does things like that, right? Every time when you email the TA GPT would immediately respond to you. And the first response is pretty much like, okay, can you clarify your question again, right? And I don't understand what you're asking about. Can you give me more detail, right? So he's very responsive. The response time is really short, right? Okay. Another TA, and you probably need several, but you probably need several emails to finish, to address your initial question. So that's TA1, right? And the second TA is pretty much, you give the TA a question, you probably don't hear from the TA for maybe 6 hours. And then maybe 6 hours later, you receive an email, step by step, address your question perfectly, right? And for the first TA, you probably take 2 days to finish addressing your problem. And the second TA take 6 hours, but within the first 6 hours, you hear nothing, and you start to worry, if he really get my email, if the TA is the ball get dropped, right? So, okay, which TA has the better response time? The first one, right? So that's the feeling of response time. So in this way, if you look at the demo again, which I just replayed, which one has better responsive time? GPT, right? ChatGPT. Okay, but what is end-to-end latency?
Which one finishes its response first?
What? How fast is to execute completely, right? Or say, I have a task, right? And in the example of TA, right? My task is that give me an answer to my lovely assignment question, right? And the first TA, yeah, the TA's response time is really short. He always responds to my email promptly, but he just couldn't address my issue until maybe the 10th email, right? So you will feel that, well, this TA is really responsive, right? That's a responsive TA. But it takes a long time to address a single issue. That's also my feeling with UCR IT. And the second one, right, the Gemini, right, it answers your question, well, it starts answering your question late. However, once it has an answer, it's just like, boom, it's all there, right? So it takes shorter amount of time for you to get the complete answer, right? So in this way, its end-to-end latency of addressing your task is shorter. Agree? So now you have the feeling, what's the difference between response time and end-to-end latency, right? The response time is the time when you submit the task. Start counting it until the first moment you feel the system, the application, is doing something for you, you receive some output from it. That's the response time. However, until the task is completely done, your task is still up and running. So from the beginning to the end of your task being addressed, that's called end-to-end latency. So in this way, end-to-end latency-wise, Gemini is better. And in terms of response time, ChatGPT is better. So that's why people, well, there's nothing good or bad about this, right? Because on the left-hand side, in the user interface design perspective, people will feel like, okay, this is more responsive, right? And ChatGPT seems to care about me a lot more than the other. And the other is really like an engineer, a robot, which is pretty much like the image of Google give others, right? So, but on the other hand, right, if I'm an engineer, time is money, right, then I would definitely feel like, okay, Gemini is what I want, right? But if you are, if you care like, okay, someone can respond to you all the time, you want a feeling of not being lonely, then ChatGPT is probably your friend. That's how I see it, right? So here's the thing, regarding response time, ChatGPT win, right? So ChatGPT, right? And for this one, throughput, who is better? What is throughput then? Oh, so end-to-end latency, right? That's Gemini, right? What's throughput? How do you define throughput?
Is it like output over time?
Output over time, right? So based on the latency of serving a question on ChatGPT and Gemini, whose throughput is better? Gemini, right? Because based on the amount of words that Gemini produces, it also includes figures, right? So the amount of data that Gemini is giving you is actually a lot more within very short period of time. So the throughput of Gemini is also better. Okay, how about the last one? Quality of results. It's hard to judge, right? So, but I would say both of them are good. So I would say C is probably the right answer. And if you pick D, I would thank you on behalf of Google because you recognize that Gemini has better output than ChatGPT, right? But that's what I want to say about, you can see, right? So there are different ways of judging performance. There are response time, there are end-to-end latency, there are throughput, and there is also quality of results that you can tell, right? So we need a definition. We need to put everyone on the same page when we discuss the performance. So there are several important performance metrics beyond the ones that I have been talking about, right? So end-to-end latency, response time, throughput bandwidth, quality of result, and in addition, from the company's perspective, companies also care about energy consumption. And the main reason is because energy consumption is directly related to electricity bills. So the lower the energy, it means that the company can pay less, right? And you might think about like, okay, company, they always give you a very ambitious vision, like do the right thing, right? Don't do evil. I didn't mean to say any specific company, right? But the thing is that their central philosophy to their success is that how can we save every penny, right? How can we spend every penny on the right place? Do the right thing on every penny that we spend, right? So for example, right, like one of the reasons that Google give people like, free food is very obvious because it makes you work longer, right? So here's the thing. The campus of Google is at the center of Mountain View. Well, not at the center of Mountain View, but on the side of Mountain View that's close to the bay, right? And then here's the thing. There aren't that many restaurants in the downtown Mountain View. And if you want everybody, we have more than 10,000 employees there, right? If you want everybody to go out for lunch, okay, it would take at least 3 hours each person to get lunch. Right. So, and after you get lunch, you have to wrap up, you have to go to the restroom. Okay, 4 hours are gone, right? And then at 4 p.m., 5 p.m., people are starting to off the work to pick up kids, right? So that's the thing, right? If you allow people, or say if you encourage people to go off for lunch, that's what will happen. So that's why company put free food there, right, to maximize the amount of work that each employee can do during the daytime, so that they can maximize the profit each employee can make, right? So you think they are treating employee better, but in fact they are doing this on purpose to save more money, right? So actually, I want to say, like, okay, a lot of things you might want to see what's the reason why behind this. And to be honest, for every company, what they really care about is the cost, the money. So energy consumption is really important because that's the electricity cost. And cost of operation, the amount of money necessary for finishing the operation, so there are two aspects of it. So energy consumption is also part of it. And the other thing is the capital cost, like how good a computer that I need to use to support this specific function. And one of the papers that I would later on put on the schedule of this quarter, if we have time, is that I would let you know how Google win the war of search engine in 25 years ago. And like right now, you think that, okay, Google is right there, it's normal, and you think Google is successful because its search engine has the best performance. But I want to tell you, that's totally not true. They are successful because they know how to save money in cost per search, right? So cost of operation is another thing. And power consumption is the heat generation produced by the circuit. So that's another metric that's also important. So if you need to spend a lot of money, well, it's about money again, right? If you want to cooling a very hot chip, then turns out that you need to put a lot of cooling cost. And a lot of data center clips that you see is that they talk about how we can be environmental friendly. So they want to build it near the ocean. But there are several aspects about that, especially these days we have the carbon tax related stuff. So power consumption is definitely something else that the company has to put into account. And again, it's also about money, right? So among this, right, so they all connect to the same thing. They all connect to the same thing. That's actually time. So end-to-end latency is how much time to complete the complete request. The response time is how much time it takes to give you the first answer. The throughput is the average amount of work I can finish within a period of time. And energy consumption is the aggregated power during the execution time. And cost operation is the amount of money to finish an operation within a given amount of time, right? And power consumption, the heat generation by the circuit, however, is also related to time. And quality of result, that's the only thing that's not related to time, right? So Or maybe, right, if you give it sufficient, how can you deliver the right quality of result within a period of time? So I would say time is the most important. And a lot of things we talk about is money, right? But don't forget time is money. Right? So time is actually related to everything. And in fact, I would say so I feel like I'm old now. So I'm in my middle age now, no matter if you can tell it or not. And one thing I realize is that you can make a lot of money, but the only thing you cannot make is time. The amount of time you have is very limited. Right? So that's why the time is so important. And that's why I'm wearing this today. Right? Life cannot be reset. Okay, so since time is so important, right? So execution time is the most essential metrics that we care about when we are evaluating the performance of a program. So that's why today, when we put the context of performance without otherwise mentioning, we are talking about the total amount of time to finish a specific task. That's the end-to-end latency. So through the reading, you must already learn how to evaluate the execution time of a CPU program. But I want to make sure that we are on the same page before we can walk away from there. So let's try this question again. And after the turbulence of login, I think you guys know how to do this now, right? So now try this question, and I will give you a good enough time once I figure out sufficient amount of you have answered. Two of you have answered. 3 now. 4. I think so.
I answered C on the last one, so.
Oh, that's you answered C on the last one. I honestly don't know because. Interesting. Okay, now it's fine. Propagation delay. Yeah, let me tell you an interesting story. So it's even worse during the fall quarter because I was in a room that has very bad internet reception. So when I have my class, I have to use my mobile phone hotspot because I have a lot of demos and everything has to go through the network. And this time they tried to schedule the same room for me, and I said no. The room just ruined my class last quarter. And I think this classroom, at least the Wi-Fi seems to be good. All right. Okay, let's see what's after the initial vote. Okay, so after the first round, it looks like B is the most popular answer, but there are some of you believe it's C or D. So why don't you go ahead and discuss with your friends to confirm what's the right answer. Go!
I messed up. I put 40, but I forgot the last term as
Still not work out for you? Still doesn't work out for you? It worked.
UCR account. So my
That's what I said. You have to log in through your UCR account.
login from that portal email and it's a login from
All right, so let's see. What do you guys have after? Okay, so looks like after the discussion, everyone kind of like agreeing the answer is B now. So I want to, is there anyone switching from another answer to B? Want to share your experience with that? Okay, what's your name? Ben, okay. What do you think?
So I put the 40-second answer initially because I thought the last term was supposed to be frequency, but it was actually 1 over frequency.
Okay, so this is, okay, so this thing is, this is the frequency, right? And why we cannot directly use frequency, but we have to take the flip?
It's just you have to cancel out the units of the first term, right?
So okay, so maybe we can go. We can put a question in this way. So what's the performance equation, eventually, that we need to use to evaluate this question?
It was I think number of instructions times CPI. I forget what it stands for. But it's CPI. And then times the 1 over the clock rate. Clock speed rate.
Right. So here's the thing, right? 1 over the clock rate is actually called cycle time.
Okay, yeah.
Right. How much time it takes for a cycle, right? So, but why do we use cycle time instead of frequency directly? So here's the thing, right? So again, why the big picture is so important? Because first of all, let's have a definition of performance. As I said, right, there are several ways of defining performance. Like the example that I gave early on, right? I can always tell people UCR is the best school, believe it or not, right? I can always tell people UC San Diego is the best school, believe it or not. I can tell people MIT is the best school, I think most of people will believe it. Okay, but here's the thing, right? You need to tell people, okay, when I say this is the best, what's the page we are on? Which page are we on? So in terms of a computer architecture, the only definition of performance, CPU performance on a program is by this, is 1 over the execution time. And why is it 1 over the execution time? Because the shorter the execution time, the better the performance from our definition. And don't ask me why that's the definition, right? And we always want shorter time because time is so precious. You cannot produce more time for yourself. You can only save more time. So being able to save time means better performance, right? So 1 over the execution time is definition of the performance. And how do we define the execution time? That's what we call CPU performance equation, like Ben, you just said, right? First of all, the number of instructions in this program being evaluated, the cycles per instruction that we need for each instruction in this program on average. And finally, how many seconds per cycle, right? And that's called cycle time. And how many seconds per cycle? That's actually 1 over your clock rate. And it's so easy to get it flipped. And here's the thing, right? You might feel like, okay, why am I always get the first wrong answer wrong? And I'm saying that don't worry about that because those questions, I designed them on purpose. I want to make you wrong. And to be honest, I think people typically remember what make you suffer a little bit more, right? Like you see a lot of like pop songs are talking about like break up, right? Instead of I'm having a happy life, right? Happy life, happy wife, something like that, right? But who cares about those songs, right? I like those songs that I feel really bad about, right? And to be honest, a lot of literature, like a lot of big like authors, big names in writing books, literatures, their life suffered, right? So what I want to say, right, is that I try to make you wrong in the questions. So then your memory will be dependent in that way, right? You will remember, this is what I got wrong last time, so I won't get it wrong next time. Right? So those are on purpose, and so actually I like to hear how you get wrong so that you will not getting wrong next time. Right? And it's okay to be wrong in a class, better than being wrong at your work. Right? So that's why we have schools. Okay, so now, and for the frequency, I have a very quick conversion. So some people are really bad at converting stuff. So I can say a quick way of memorizing it. So typically, like right now, the processor is typically at the gigahertz level. So if you are at 1 gigahertz, it's typically 1 nanoseconds per cycle. Right? So if it's 1 gigahertz, it means your cycle time is 1 nanosecond. And if it's 2 gigahertz, it means half nanosecond. If it's 4 gigahertz, it means it's 1 over 4 nanosecond, right? That's 0.25 nanosecond. And now, the second question you might ask is that, okay, why this equation is defined in this way? Why is IC times CPI times CT? Then that goes back to the big picture that we have been talking about. So that's why big pictures are so important. Remember, this is von Neumann architecture. Right? And how von Neumann computer execute your program is that I have the processor. And don't forget, any digital circuit, it operates based on clocks. So every operation is driven by the clock. So every operation is counted by clocks. So that's why there is a factor called clock cycle time there. Right? How much time it takes for each clock cycle to execute. And within each clock cycle, it will get something done. And sometimes each single instruction would need multiple cycles to get it done. So that's why the cycles per instruction is not always 1. Sometimes it could be larger, sometimes it could be lower, right? And okay, the next thing is that how many, because we execute this program instruction by instruction. So it actually matters how many instructions we have to execute in total. When I say instructions here, it's actually the dynamic instructions, which means how many instances of instructions that you will need to execute in your program. So that total means the instructions per program. So how many of this and how long does it take to execute an instruction would actually give you the execution time. So if you put all of this together, it will tell you I have a total of 5 times 10 to the 9 instructions, and 20% of them would take 4 cycles, 20% of them would take 3 cycles, 60% of them would take just 1 cycle. So that gives you an average CPI, and if you put it all together, it will give you 2.5 seconds. Okay, so now let's practice one more time with more realistic context. So I'm giving you this C code, and on the right-hand side is x86 assembly. So now I want you to evaluate if the count is set to 1,000 million. Memory instruction takes 4 cycles, branch instruction takes 3 cycles, outer instruction takes 1 cycle on average. How much time would it take? That's why we wanted to preview the x86 handout, right? So you know what is memory instruction, what is branch, what is others. All right, so for this particular question, let's go ahead and jump directly to group discussion. So why don't you grab a few people around you to see what answer do you guys have? All right, let's see. What do you guys have after discussion? All right. Oh boy. So we have answers from A, B, C, D. Very strong diversity, which I like. So now, can some of you tell me how to tackle this kind of question? I can tell you one thing. You will see one similar on your midterm for sure. So now everybody is quiet and paying attention, right? Okay, how to tackle this kind of question? Some of you would like to try. Okay, what's your name? Clarity. Yeah, I remember you. I like your name with a lot of clarity. Okay, what do you think?
So, as far as I can tell, it's like the same question as the last poll, just like
The same question in what way?
in the terms of you have you have these 5 instructions. 20% of them have a CPI of 4.
How do you know it's 20% of them?
So there's one memory instruction. That's
Okay, there's one memory instruction. Which one?
the move LS.
Okay, so this is a memory one, right? How about the second one?
Then there is the JNE at the end. So
Uh-huh.
that's one branch and jump.
So that's a jump, a
Yeah.
branch, right? This is actually branch,
Yeah.
right?
And then the rest are all a CPI of 1.
Okay, why?
Because they're not memory instructions, they're all operating on the registers.
Okay, so they are all arithmetic operations. Well, so I would say, okay, if you want to count them in detail, these two, they are arithmetic, right? And this one specific, a lot of you get confused about this. This is logical operation, right? But what does that mean is that no matter it's arithmetic or logical, they are not either memory or branch, right? Okay, but now where the 20% comes from?
20% is 1 over 5.
1 over 5. But are they executed in equal amount?
They're going to be so it's going to be executed, I think, all of them until it gets so executed in order until it gets to the jump, and then that jump will go back to the beginning, and that will happen 1 billion times. And so whether or not, I don't recall if that last one would count in the last thing, but at that point it's kind of a rounding error.
Okay, so here's the thing, right? So this x86 actually implements the C code, right? So you can, and a reason why, okay, so first of all, I want to say the purpose of this class is never asking you guys to program at the level of assembly, because I'm not a believer of Dijkstra, von John von Neumann in many ways. Like my PhD thesis is actually talking about data flow architecture, which is a non-von Neumann architecture, because von Neumann architecture has too many issues. But set it aside, right? The left-hand side actually tells you what I want the right-hand side behavior to be. So when I say it's 1 billion in this count, you can assume there is a loop on the right-hand side would be executed for 1 billion times. And where the loop begins is actually between this L3 label and the JNE operation. So every time you execute this JNE, you know if I want to continue in this loop or not. So if I said it's going to be 1 billion, these 5 instructions, they will be executed in 5 billion times. So that's why the total instruction count will be 5 times 1 billion, which is the same number that you got as the last question, right? And it's also a coincidence that one of them is a memory instruction, so 1 out of 5, 20% is a memory instruction, which 4 cycles, and the branch 3 cycles, 20% of them, right? So that's why I was assuming that, okay, if you get the previous one right, this one you should get it right, right? And at some point you will figure out, okay, these 2 questions, they are identical, right? Now you see it. Okay, so hopefully you will get it right. So but the big takeaway here is that, okay, 3 important elements are affecting our performance. The first is the instruction count, and the second is the cycles per instruction, and finally, the cycle time. So 3 big factors are affecting the total execution time of your program. So now, let's discuss what would affect each term in the performance equation. So the first one, and the big motivation why we want to put CS203 as a core course for computer science curriculum is because programmer actually matters in many aspects of performance. So can you tell within the 3, how many can you guys affect? The first one should be an individual one. Yeah, individual thinking. All right, let's see. So in the initial vote, okay, we see 2 popular answers, B and C. So why don't you go ahead and discuss with your friend for another 90 seconds, and let's see what you guys have after discussion. B and C, huh?
I was thinking that
All right, so after the first round of discussion, now 67% of you think the answer is C, 30% of you think the answer is B, which means only 3% of you think it's D. So why don't we take a look? So right now, I want to show you a few demos to give you some evidence regarding the true answers. But before that, we are holding off the answer right now. So first of all, right, one of the examples that I want to give you is that here we have 2 programs, A and B. Right? We have 2 programs, A and B. And can someone tell me about the complexity of these 2 programs? Both are n squares, right? So they have no difference in complexity. How about the result they produce? Are they going to be the same? They are identical, both in terms of algorithm and functionality, right? So let me show you the demo regarding their performance. So again, like this is the same Jupyter Notebook interface that you'll use for your homework. And one thing, a lot of things that you can use from the Jupyter Notebook, and on the file browser of the Jupyter Notebook, you can also launch a VS Code if you want to edit on your homework, and you would launch. So this is basically a Docker container for you to work on your project, a lot of stuff. So it's very convenient, and if you haven't tried it, you should try it. But in your homework, you will have a similar notebook like this. So right now, I'm going to show you, we have a program that is this one, which is well, ignore the initialization part. The main loop is actually identical to the slide that I showed. And right now, I'm going to run this program and let you see what the performance looks like. And when I talk about performance here, I'm using a program called perf. And this is a Linux built-in program which would give you the performance counter, which tell you the instruction count, the CPI. Well, they use IPC, which is the flip of CPI, very annoying, and cycle time on average when you run this. So now, if you look at that, for the version A, which is the left-hand side, start with I and then J in a loop. You can see the execution time of that is 0.8. Okay. So do you think version B will be the same or not? Bit different in what way? How different? Oh, okay, you already see that, right? Version B, 1.5 seconds. Twice more than version A, even though they are algorithm-wise identical, functional-wise identical. So now my question would be, why? How many of the following make the performance difference between version A and B? Why their performance are different? Individual thinking. Right? If you ask your teacher in CS 218, they will tell you it's the same.
Yeah, I think it's because.
Well, yeah, answer it. Isn't that fun? Seeing a lot of things that are not that trivial when you program. Okay, so now the initial both shows the answer is B. So why don't you go ahead and discuss with your friend regarding, so B only says 1, right? What's that one? What?
Do you have to get the questions right for participation?
No.
Okay. Okay.
All right, so after the discussion, well, I know the answer is B, but which is that one? CPI. Okay, so these two programs, they are the same. They have the same iterations of the loop, and the inner iteration has nothing different, right? So we can imagine, first of all, complexities are the same. Instruction count is the same. The same processor, and we don't do anything fancy to change the clock rate. So it's always the same. So actually the CPI is the one make difference. And again, we can use the program called perf to see what's going on there. And in fact, when I have the previous run, it actually, if you overthink it, you already see that, right? So first of all, both of them have 16 billion instructions, right? Pretty close, right? The number of branches are the same. However, I think there's somewhere talking about the IPC CPI. Do they have it? Okay, so another thing, okay, if you don't have the CPI, right, you can divide that like cycles and instruction because that's cycles per instructions, right? So this one takes 4 billion cycles, but this one takes 7.4 billion cycles, right? So instruction count, not too different. Cycle time, about the same, right? 5.1 gigahertz, 5.1 gigahertz, right? So the only thing that makes difference is actually the CPI. Okay, so now let's go to another example, which we already seen before. So this one, right, that's actually one of the bazaar you have for the algorithm complexity. Why am I adding this order unlock and would make the performance better? Why the performance is better when I have this sorting? Think individually. All right, the first run, okay, we got two answers, A and D, right? So I love this. You know, it's like election, right? So we definitely want some debate between these two parties. So why don't you guys debate with each other during this 90 seconds, A or D? right, let's see what you guys have after initial run. Okay, so some more of you think it's A. Some of you still insist it's D. So I want to invite one group advocate for A and one group advocate for D to tell me about why. So let's start with who advocates D. You just guessed.
Yeah, I don't know.
Oh, we're A.
We are A. You are A. You are.
I choose D.
You choose D. Okay. What do you think?
Actually, I was like not sure about the question. Is that we only choose the good part for the performance, or
So achieve better performance.
okay? In that case, I think only the CPI.
Okay,
Make it
so here's the thing, right? We know the programmer changed the instructions count, right?
Yeah.
Because adding a sort is by anyway, we are adding the instruction count. Agree?
Yeah.
Yeah, because you are executing more. You are doing more stuff. You are doing extra stuff. But the performance is better,
Yeah.
right? So if you think about the performance equation, right? More instruction count means more time. So the performance is going to be worse. It's the same processor, so there must be something going into the better way. That's actually the CPI. So this is a case where, as a programmer, you change both the instruction count and CPI. However, you change the instruction count in a bad way, but make the CPI toward a good way. Very strange, right? Okay, question? You don't understand how the CPI is better, right? How is this better? And the answer is there is something called branch prediction in your microprocessor. So this is only true with modern processor. So if you ask this question 40 years ago, it's not true. But right now, if I ask you this question, that's why. And we will tell you about the magic of branch prediction after midterm. But here, you just need to know that there is no absolute relationship between instruction count and a CPI. So sometimes you have more instruction count, doesn't mean your performance is going to be worse. And sometimes you have fewer instruction count, but if you chose the wrong instruction, that will make your instruction program performance worse, right? And algorithm complexity, they care about instruction count, but they ignore the fact that there are some more time-consuming ones that could be more efficient. And one last thing, programmers can actually set the cycle time. And that's actually something in your homework that you can tell. So, oh boy. Okay. Why is it asking me for the UCSD one? Is this right? Okay, here we go. Okay, so what? Hello? Okay, so this is the assignment 2, which is going to be released later today. And in assignment 2, right, I will show you as a programmer, you can actually change the cycle time. Okay, so here's the thing. In the assignment 2, 5.4 section, you will experience that, okay, the processor has a few different frequencies, and you can actually intentionally change the cycle time in a certain way. Okay, let me do this. So, for example, here I can run, boy. Hello? No, okay. Sorry, I have to build it all the way up. Okay, so one trick about this assignment is that you have to execute from the beginning. So let me see. Okay, here we go. So that's the beginning. And so So I get the program built, and then, what? Okay, you will experience that in your assignment later. All right, but one thing I want to say is that programmers can actually change everything. All right, so before you leave the classroom, there are several things that I want to mention. Oh boy. Okay, so actually, oh boy. Okay, here we go. So before you leave the classroom, I want to tell you, first of all, the assignment 1 due on April 11th, and you need to complete the course agreement, and it would typically take 1 to 2 days to get your agreement and account activated. So act early as possible. And one thing I want to say, this time, because we have fewer TA supports, and I'm a very optimistic person, I take every challenging as a turning point. So this time we make all the assignment auto-graded, even including your writing part. So what does that mean is that you can keep improving your writing until you receive full credits of your assignment. So if you start early, you submit early, you are more likely to get 100%. And when you submit, you will get immediate feedback, which question I get wrong, right? And what's the direction of making it right. Okay, so start early, submit as early as possible. And we don't have reading quizzes next week because every time when we have a reading quizzes, it's covering from the due date of the reading quiz till the next due date. So it will cover several lectures. And this time we actually cover the material next week as well. And also check our website for slides, grade schedules, Gradescope for quizzes, assignments, Piazza for discussion. And if you didn't attend a class and you miss it, you want to recap on it, we have the YouTube channel. Other than that, enjoy the rest of your week. I will see you next Tuesday.